All right, so we're gonna start this will be the second chapter, so chapter 2. A multi-degree of freedom systems. Okay, so basically what is the type of system we're gonna have? I hope by now you can have this figured out, is that you need the degree of freedom generally is defined by the number of masses. All right, so let's do a general case. Those two masses are connected by a spring K2 and a damper C2. Let me do some wheels, otherwise I didn't put this at the right place. And now let's say also that these two springs are connected to the end by a spring and a damper. Okay, we assume no friction. And to make this as general as we can, we're going to say that in here, this is subjected to a force F1. This is subjected to a force F2. And this will be the origin of our coordinate system x1 of t. Up or down? I don't know how do you say that. Down. I don't know. Would be up or down? What is that? I don't know. There's some stuff in English. Language I haven't had that. Is that when you need to turn something on for me, yeah, they say turn it off. Oh. Wait. What language is he now? No, I mean it's like I mean, how do you say did you turn the switch on? I mean to me, or I don't remember exactly an example, but it's something about on off that is on the reverse order. I need to think about it. It's like now the screen, you know, it's like put the screen up. I understood, but it's like, is it really up or is it really down? You know. I mean, anyway, so if we follow the normal procedure, what are the steps? Correct. So step one, some type of figure, free body diagram. Okay. Okay, so in this case, yeah, I might do maybe, I don't know, to do this right now. So be careful because I might do more than one free body diagram, okay? So one for the understanding of the figures. So over here, let's start by M1. Okay, so let's see, what would be the forces acting on M1? K1, X1, and Yeah, we'll start by the left-hand side. So wait, well, I forgot to put the x1 here. And this will be x dot 1. Okay, so imagine this, that initially we move, oops, hold on 1 second, this should be M1, and this should be M2. So initially, I imagine that I move this a little bit to the left, okay? Or to the right, I mean, it doesn't matter. But let's say the force, if we move it a bit to the right, it will be moving that way. Now, that's the only reason why I'm doing this figure. This spring here will be creating what force? Will be K2 what? X2. Okay, but X2, but also this one will be moving, no? So that one will be moving what? X2 minus X1, because it will be the relative motion, no? Between both of them. So now, basically, this one is doing this force. It will be the equivalent force on M2, but going in the opposite direction, no? Yes? Okay. And here we'll have basically exactly the same thing with the acceleration, with the damping will be x dot 1 minus, x dot 2 minus x dot 1. And then at the end over here, we'll have, that one is easy, K3 x2 C3 x dot 2, no? So I'm just doing this one for this figure, but really the figures that we need will be which one? The ones we have been doing. So really the figures that we need that we have been doing for the other ones would be like, we need one figure for each mass, okay? So basically, if I just copy the forces, it will be even more forces. We have here K1 x1, C x dot 1, K2 x2 minus x1, C2 x dot 2 minus x dot 1. Am I leaving any force? Yeah, probably a bunch of them. Which ones am I leaving out? We say no friction, but I will still missing some forces. So we'll be missing F1 of T, no? If you want, we can still be missing M1G, no? And we could be miss the normal force. Okay, and we say no friction, no? And then on the right hand side, what type of motion would this have? Just translation, no? Okay. So I don't know if I forget something. So now we do exactly the same thing with the other one. So that's what I'm going to recopy from the figure here. We're going to have here K2 x2 minus x1, C2 x dot 2 minus x dot 1. Then on this side, we have K2 x2 minus x1, C2 x dot 2 minus x dot 1. It will be moving M2 x dot 2. We could put the same thing as before, the force F2 of T. M2G, I'm going to call this one N2, and the other one I just add the one for N1 and 2, no? But basically, we don't really need them. So basically, you see that it's the same thing that we did for 1 degree of freedom, no? Can I move on or?
For M2 on the right side, it also has K2 X2 minus X1, should not be K3 X2.
Oh, yep, you're right. I didn't pay attention. I should be K3 and C3.
Yeah.
Yeah, thank you. So now what should be step 2? Write down the equation of motion by writing Newton's equation. First, what type of motion is this going to have? Translation, okay? So that's what we're going to be doing, but let's think a little bit ahead. All right, let's see what the math needs to give us at the end, okay? Other point. So what could be the different type of motions that these two masses could exhibit? Just think about the real thing. What could happen to these masses? Either they are moving together, yeah? Either they're moving away from each other, or maybe one is moving one direction, the one is moving the other direction, no? Yeah, or I mean, either they're moving together or either they're moving away from each other, no? Basically, those two types of motions we can have, no? So what we need the math is to be able to give us that, correct? Agree? All right. So, all right, so the first thing will be, which is the difficult part, will be step 2. Which is when we find the equation of motion, we apply Newton's equation, because it's my favorite one, but you could use the Lagrange if you want, no? Yeah, but I like Newton's. There's no, I don't know. So basically in this case, it's going to be what? Since it's only translation, we can just use summation of forces equals to MA. All right, so we go from the figure, everything comes from a figure. If I look at figure 1, let's see, so I first do summation of forces for M1, let's say A1. So this should be equal to what? Let me start from this figure. So let's see, it will be F1 of T minus K1 X1 minus C1 X dot 1 plus K2 X2 minus X1 plus C2 X dot 2 minus X dot 1. And this should be equal to what? M1 X dot 1. Okay, so let me just rearrange this equation. We can rewrite this equation as M1 X dot 1 plus C1 X dot 1 minus C2 X dot 2 minus X dot 1 plus K1 X1 minus K2 X2 minus X1 equal to 1 of T. And let's say that will be our equation 1. Okay, next, what can we do? We can do exactly the same thing with our second thing, which will be this one. So basically, it's going to be kind of a similar equation. So we have what? F2 of T minus K2 X2 minus X1 minus C2 X dot 2 minus X dot 1 plus K3 X2 minus X1 plus C3 X dot 2 minus X dot 1 equal to, oops, sorry, I was just copying what's above, equal to what? M2 double dot 2. Or I can just rewrite it as M2 x double dot 2 plus C3 x dot 2 plus C2 x dot 2 minus x dot 1 plus K3 x2 plus K2 x2 minus x1 equal to F2 of t. And this will be our equation 2. Okay, so next we can say the system of 2 degree of freedom is modeled by equations 1 and 2. You want to put comma that can be written as M1 x double dot 1 plus K1 plus K2 x1 minus K2 x2 plus C1 plus C2 x dot 1 minus C2 x dot 2 equal to 1 of t. M2 x double dot 2 plus K2 plus K3 x2 minus K2 x1 plus C2 plus C3 x dot 2 minus C2 x dot 1 equal to F2 of t. Okay. So basically, as we said before, these are second order differential equations. You see the x double dot, no? Okay. So in order to do this, probably you did the same thing in a differential equation. We're going to rewrite these two equations under the form of a matrix. So let's say, or in matrix form, we have what? M1, 0, 0, and if you need time to figure this out, let me know. Okay, I'll give you time to think about it. Will be x double dot 1, x double dot 2, plus C1 plus C2, it should be minus C2 minus C2, C2 plus C3, x dot 1, x dot 2, plus K1 plus K2 minus K2 minus K2 K2 plus K3. X1 2 equal to F1 F2. So please, guys, pay attention to see if you need sometimes to see how I went from these two equations to this matrix form, no? So do you see how I went from here to here? Yes, everyone? All right, so that was step one. Step two, now if we want to solve this, what do we need to do? Let's say this will be step 3 in order to solve this type of problems. What do we do, John, in order to solve this type of equation? What have we been doing so far all the time? Yeah, nothing's going to change. Assuming harmonic solution. So basically, what was the general form of our harmonic solution? Was X equal to capital X E lambda T, no? Okay, but in this case, this is the assumed solution. So basically, what does that mean? That really what we're going to have is what? X, we assume one solution for X1 of T, no? That should be equal to capital X1 E I lambda 1T, and another one that will be other form, capital X2 E I lambda 2T, no? Let's just put here lambda. We'll figure out. Yeah, okay. So we figure out that later. Plus lambda per lambda T. Don't put lambda 1, lambda 2. We do that a bit later. It will be lambda 1, lambda 2. Let's keep it this way. So now, what is step 3 or step 4? What we need to do now? We take the second derivative. No. Well, first we take the first derivative for this term. We take the second derivative. And what do? We substitute into this equation. So let's say, let's call this equation 3. I think this is still the next step 4, doesn't matter. Step 4, what do? We substitute assume solution into equations of motion, which is equation 3. So if we do the substitution, okay, what are we gonna get? So let's see. So done this a little bit differently, but it's fine. We're gonna get here minus M1 lambda, don't put lambda 1, lambda square plus K1 plus K2. Here we're gonna have minus K2 here we're gonna get minus K2, and here we're gonna get minus M2 lambda square plus K2 plus K3. I'm gonna close the matrix times the capital X1 capital X2. Close the big bracket. Okay, so really here we are solving first for the free vibration problem, assuming F1, F2 equal to 0. Yeah, it's fine. But basically, please spend a minute to know how did I to do the substitution, okay, in your head if you want. Okay, what would be the first derivative of this one? Will be I lambda, correct, will be the I x1 exponential, I mean, we have the I lambda x1 exponential of, and then will be, second derivative will be minus lambda square, no? That's why we have here this term minus lambda square, no? One for M1, one for M2. Then you see this one in function of X, so which are just in function of X1, X2, and the E lambda, no? Yeah. So in this case, if you want, let's add it, because that's really what we're doing here. We're not doing the forced vibration. So assuming solution for the case F1 of t equal F2 of t equals 0. We are doing the free vibration problem, not before doing the forced vibration. Let's see if you understand now what we have been doing. What's going to be the only difference once we solve the forced vibration problem? So meaning that F1 and F2 will be different than 0, and we have also some type of harmonic, expression. What's going to be the only difference? The only difference is going to be here. And what is it going to be? What is lambda in this case here? I mean, you're going the right direction. So basically, when I use lambda, I'm talking about this is going to become the natural frequency. Correct? The frequencies at which the structure is going to vibrate. So basically, the frequency, so it should be one frequency at which these two objects are going to move together. And it's going to be a frequency at which these two objects are going to move away from each other. Okay? But that's the natural frequencies. Once we will have, let's say, the frequencies of these forces, we're probably going to give the solution in function of the force frequencies. Yeah? Okay, that has been the only difference we have been doing, no? For 1 degree of freedom. All right. So, we come here. All right. So let's say here I'm going to put over here. So generally we say what? The above equation is satisfied if and only if what? When will be this equation satisfied? So we can have one where the two x's or the a lambda, you can put lambda will be equal to 0, no? We did that for 1 degree of freedom. How did we call that equation, that solution? Okay, trivial solution. Or now it's not as trivial as before, because before the only thing we'll say is then when the term inside the bracket is equal to 0. Here is basically the same thing, but the term inside the bracket is a matrix, no? Yeah? Okay. Or so when we're gonna have the term inside the bracket, but it's going to be something up front, M1 lambda square plus K1 plus K2 minus K2 minus K2. Actually, we could do it that way. Minus M2 lambda square plus, oops. Let me do it this way, plus K2 plus K3. Is equal to 0. So what do we need to do in order to solve for this equal to 0? What is the mathematical stuff you have been doing? I mean, basically, this will have a solution when the determinant of this matrix will be equal to 0, no? Okay, so we can say here, from here, we're going to take the determinant, basically, of this matrix again. So M1 lambda squared plus K1 plus K2 minus K2 minus K2 minus M2 lambda squared plus K2 plus K3. Okay, so how would you do the determinant? This will be minus M1 lambda squared plus K1 plus K2. You multiply by the other one, minus M2 lambda squared plus K2 plus K3 minus, what did I do here? No, that's fine. Minus, so this will give minus, minus will be plus, but you have the minus, no? Yes, yeah. Equal to 0. So basically, if you do a little bit of the algebra, you can rewrite this as M1, M2, lambda to the 4th, minus K1 plus K2, M2, plus K2 plus K3, M1 lambda square plus K1 plus K2 times K2 plus K3 minus K2 square equal to 0. Obviously, I'm skipping some algebra, no? I mean, all this stuff, I'm doing this now, you know, symbolically, but once you have computers, you solve this so quick, okay? Yes. So basically, does anyone remember the name of this equation? How is this equation called in mathematics? This now is known as the characteristic equation. Okay, so now pay attention. So here this solving the characteristic equation for lambda square, the two natural frequencies of the system are obtained. So basically, if we solve the above system in lambda square, yeah, this is the variable. So what would be this one? This will be lambda square to the square, no? And this will be lambda, correct? So this becomes like a quadratic equation, yes, where the solution will be given. So let's say here we'll have then lambda 1 square will be equal to omega 1 square, and lambda 2 square will be equal to our omega 2 square, where remember omega is the natural frequency. Which omega? The capital omega, no? So I think, yeah, I don't know exactly what the reason is. I mean, because omega, this is capital omega, this is omega. So on the notes, what I'm using is this lowercase omega as the natural frequency, and the capital omega as the force frequency. So, but different books might do something different, okay? But do you understand the difference between the natural frequency and the force frequency?
I figured natural saying natural frequency.
Oh yeah, I see, yeah, correct, yeah, I've seen that stuff as well. Correct, yeah, correct, I understand. Yeah, I like more the term natural frequency than rotational frequency. Tell you what you refer to. Okay. So now, step 5, which is we need to be careful. Solve again problem. Okay, so do you remember that we say that this equation here has a solution when either x1, x2, or if you put the lambda equal to 0, which is the trivial solution, or when this is going to be equal to 0. Okay, but in order for this to be equal to 0, we first need to solve for the determinant. And from the determinant, we find the value for lambda squares, which are our natural frequency. But let's not forget that our initial condition is what? Is that this equation here needs to be equal to 0. Correct? So now we have two cases, no? Because here we have lambda, but lambda can be equal to what? Lambda 1 or lambda 2. Correct? And this should give us different solutions, no? Okay? Yes? Okay. So solve again problem. So let me start here. So recalling that the non-trivial. Solution requires that minus M1 lambda plus K1 plus K2 negative K2 negative K2 minus M2 lambda plus K2 plus K3 X1 X2 equal to 0, no? So what did we just say is that, oops, I forgot to put the square, so right, so fast, so square and square. All right. So now what's happened is that we know that here for lambda, we have two choices. We have lambda 1, lambda 2, no? Lambda 1 square, lambda 2 square. So we need to solve for each one of the cases. So let's say case 1, let's say our lambda will be equal to the lambda 1 square. Lambda square, sorry, will be equal to the lambda 1 square, which is really our first natural frequency. So basically what I was saying is that at that frequency, we need to know what's going to happen, no? So at that frequency, what should the math give us is that either these two masses are moving together or they are moving away from each other. Yeah? That's what we should get from the eigenproduct. All right, so let's see what happens. So we do this, we're going to get that. So we get that minus M1 lambda 1 square plus K1 plus K2 negative K2 negative K2 minus M2 lambda 1 square plus K2 plus K3. Equal to X1, X2 equal to 0. Now I'm going to move back to the, really all this stuff, once you have the computers and you have values, you're going to have to do it, okay? Or I can rewrite this as what? As minus M1 lambda 1 square. So I do the reverse. We were in matrix form. I'm going to move this out of the matrix form. X1 minus K2 X2 equal to 0. And this one will be minus K2 X1 plus minus M2 lambda 1 square plus K2 plus K3 X2 equal to 0. Okay, so I'm going to stop here for a second. Let me know when you're done doing this. Okay, so now from either one of these equations, I'm going to solve for the ratio of x2 over x1, or you could do the other one. So let's see, if we look at the first equation, what would that be? X2, if we move this one, will be K2 X2 to the other one. Yeah. Okay. So we're going to have what over here? what should it be? If we look at this one, then we're gonna have here K2 dividing, and here we're gonna have minus M1 lambda 1 squared plus K1 plus K2. Yeah, from the top equation. Okay, so let's say, let's call this one I. Let's say this comes from I. And from the second equation, what we're gonna have, so will be reversed, will be K2 will be equal to minus M2 lambda 1 square plus K2 plus K3. Okay, so now just to refer that this is to case one. Okay, so this case one over here, I'm going to put this way, okay? This will be case one. And this will be from 2. Okay, so now we need to do case 2, so will be lambda square will be equal to lambda 2 square. So, I mean, if you want, let's just do it very quick. Let's just copy everything again. So we'll have what? Minus M1 lambda 2 square plus K1 plus K2, negative K2, negative K2, minus M2 lambda 2 square plus K2 plus K3. X1, X2 equal to 0. Or I just write under the same formula here will be minus M1 lambda 2 square will be, everything will be identical. The only thing you need to change is the sub-index for the lambda. Okay, and minus K2 X1 plus minus M1 lambda 2 square plus K2 plus K3, X2 equal to 0. Okay, so basically we're gonna get the same expression as this one, but instead of lambda sub 1 is gonna be lambda sub 2, no? Okay, let me just copy that expression. So we're gonna get x2 over x1, but this time I'm gonna put the 2 on top to make sure that this is for case 2. And this should be equal to what? Minus M1 lambda 2 square plus K1 plus K2 over K2, K2 minus M2 lambda 2 square plus K2 plus K3. Again, this is MATLAB does all that stuff for you, okay? But at least you need to see it once, no? That way. Hey, MATLAB does it, yeah, MATLAB does it for you, but you probably don't have to do one on the exam by hand, no? With values. Okay, nothing but. Okay, so let's do a little summary here of what we have been doing, okay? So summary of eigenproblem. Because here the physical meaning of the term is important. Okay, so let's see, the lambda 1 square this value is known as the eigenvalue. Okay, so it's called the eigenproblem. And we said that this was equal to what? Omega n2, which what is this one? The natural frequency. Okay, so I can put here, let me just put here similarly, I can put it right by the side. We have lambda 2 square will be equal to omega 2 square, no? So the conclusion here, which is important, is to say that to understand is that the eigenvalue basically is the same thing as the natural frequency. Okay. Now the other thing we did is we did x2 over x1. We put a 1 over here, no? Yeah. So remember, this is for lambda square equal to lambda 1 square, no? Okay. So this term over here is what is known as the eigenvector. Okay, and let me do this one if you want here in parallel, x2, x of 1, 2. That 2 is for the case lambda square equal lambda 2 square. So again, this is the mathematical term is called eigenvector. Okay, but in vibrations or structural dynamics, okay, in vibration, the eigenvector is generally named as the mode shape. So I'm going to put over here eigenvector equal to mode shape. So basically, what is the mode shape? Okay, here without values is difficult to understand it. Okay, but as soon as we put the values, will be very easy. But let's say here, what should happen if we put values in this equation? Okay, is let's say we get x2 over x1 equal. I'm going to make it up completely. I mean, let's say here that if in our system, okay, let's make it easy. Okay. Obviously, it's going to depend, but let's say if in our system, M1 equal M2, K1 equal K2 equal K3, C1 equal C2 equal C3, no? To make it symbolic. So basically, the two options we can have is that if X1 will be related to the X, no? X2 will be related to this X. So if X2 over X1, the ratio is equal to 1, what does that mean? Is that when one is moving 1 unit to the right, the other one is going to be moving 1 unit to the right, no? Yes?
Yeah.
Does that make sense? So that we call eigenvector or mode shape. Now, what's going to happen probably in case 2 is that the ratio given by the case 2 here, x2 over x1, will be equal to -1. So if it's equal to -1, what does that mean? Is that those two move to the right. So basically, we're trying to say, okay, so if it's equal to -1, x2 equal minus x1 or minus x1 equal minus x2, no? Yeah. So if this one is moving 1 unit to the right, this one will be moving 1 unit to the left, or if this one is moving 1 unit to the left, this one will be moving 1 unit to the right. Okay. But what's important is that each one of those two motions, eigenvectors, mode shapes, corresponds to one eigenvalue, one natural frequency. Correct? So this one here is going to correspond to lambda 1 squared. So we can say at the natural frequency lambda 1 squared or omega sub 1, if the system reaches that frequency, how are the two blocks going to move? They're going to move in together, no? If we reach the other frequency, then what's going to happen? They're going to move in opposite direction. Yeah, does that make sense? Okay.
The concept makes sense, but then the values, the absolute value of lambda 1 and lambda 2 would be.
No, absolutely not. No. What is omega? That let's say that to talk in hertz instead of radians per second, you might have that at 2 hertz, the two blocks are going to be moving together. But let's say lambda 2 is 5 hertz. At 5 hertz, they're going to be moving away from each other. Yeah. Okay. Yeah, sometimes easier to see at the structural point of view. If you think about it, sometimes on a structure, I mean, this is not a good example, but I mean, sometimes if this is vibrating, okay, if this is vibrating slowly, it's probably going to vibrate just up and down. I mean, I don't want to see that much, just up and down, no? If you start increasing the vibration, what's going to happen to this? Now it's going to vibrate this way, no? I mean, what I'm trying to say is, you have the same thing in vibration, so let's see. Let's say you have a beam. It's easy to see as a cantilever beam. All right. So let's say, and generally it goes from minor to higher frequency. So this can vibrate this way, up and down. Correct? Let's say at lambda 1 squared will be equal to omega 1 squared. You agree that this could also vibrate, if this is our original beam, this could also vibrate something like this, no? If you increase the frequency, correct? So at lambda 2 squared, this will be omega 2 squared. So they're not equal at all. That's the stuff. And even if you keep increasing the frequency, then this can vibrate what? Instead of having 2, you might have 3, no? Okay, and so on. Does that make sense? Okay. So one structure has an infinite number of motions. But when you model it, when you do the modeling, let's say something like this with say 1 or 2 degrees of freedom, then you limit the number of motions that you can have. So in this case, 2 degrees of freedom is going to be able to have 2 different eigenvectors or 2 types of motions. I mean, not always, because sometimes in some cases, if you put the values, they might only be able to do 1 motion, no? You might have 2 repetitive eigenvalues, which is possible in math, no? You can have two repetitive roots for the characteristic equation, no? Okay. Okay. Now the rest is a bit of complicated formulation. So what time is it? Okay, so this was what? Last step 4? Step 5? Okay, so here I'm going to put a step 6. And this is the part that generally creates problems. Okay, so the final response of the 2 degree of freedom is obtained by doing what? What did we do before? What do we need to do? I mean, now that we solve for the lambdas, for the frequency, we need for the lambda, we need to go back and substitute into the assumed solution, no? Which is what we did, no? Okay, so we say that x of t, I'm going to simplify it too much. Yeah, I'm going to oversimplify it probably. So we had this was equal to this now. Yeah. So in our case, let's say we'll have what? X1 EI lambda 1t plus X2 EI lambda 2t. Okay, and here I'm going to put where I really just do an example where X1 and X2 are 2 constants to be determined from what? What is IC? You have space probably. I don't have space to put it. What is IC stands for? What does IC stands for? From initial conditions, no? I mean, this can become a lot more complicated because now you can write this as the ratio of x1 over x2 and so on, no? But I'm just going to keep it simple. Oh, and one more thing that I forgot to mention, I just noticed now. Okay, if we go back to this equation here, I just want to be accurate on the notes. Assuming I'm a solution for, we say there is no forces, correct? And also, if you look at the solution, we didn't put damping, no? So we only solve the free vibration, okay? I just want to mention that over here. So this is the free vibration plus, which is for the natural frequency, the same thing. Okay, so maybe open MATLAB. I'm going to do one quick example. We have time. 1, 2, 3, 4, 5. All right, so let's do here. example. So in our example, let me do a quick figure. Okay, so for this problem, let's say we're just going to say M1 equal to M, M2 equals to 2M, K1 equals K2 equal to K, and K3 equals to 2K. And because in MATLAB we need values, let's just say the simplest case we can do, M and K will equal to 1. Yeah, I'm not going to rush too much. Okay, so, okay, instead of saying, so if we need to find the equation of motion, you need to do the feedback diagram and so on and so on. But in this case, since we already did all this stuff, and basically, you know, you can use this equation, okay, or you follow the same process. So we can take this equation here, no? Yes? This will be 0, no? There's no damping. M1 will be equal to M. M2 will be equal to what? 2M. And then we know that K1 plus K2, then this will become what? 2K? No? Okay. So let's say using this equation here, all right? So the equation of motion, the equations of motion in matrix form are what? We have M 0, 0, 2M, X double dot 1, X double dot 2, plus 2K minus K and 3K X1 X2 equal to 0. All right. So, or this, if we put the values, this would be equal to what? 1, 0, 0, 2, X double dot 1, X double dot 2, plus what? 2, negative 1, negative 1, and 3. X1, X2 will be equal to 0, 0. All right, so let's see how the bunch of. Okay, so I'm not going to be able to finish everything today, but at least we start. Let's go to MATLAB. I hope we can reach what I want. Probably we will. And then we can spend tomorrow time in class to talk about that.
Come on, Madlam. Okay, so really, I just want to do very quick the eigenvalue problem, and then we'll solve it in the, and then tomorrow we'll spend a bunch of the class talking about it, okay? So we can eliminate this one, okay, so new script. So let's go over here. You know, I like to always clear everything, clear all CLC. And let's say this one will be again problem, or let's say 2 degree of freedom. Okay, might do both of them. Okay, so let's see. The first matrix that we have, this one over here, okay? Let's call this matrix M. All right. So, and let's do it general. So let's say M, the big matrix, if we look at the one we had, let's say was equal to what? If we look at this equation here, I'm going to use this one, okay? This notation. M1, 0, I do the first row, and then it will be equal to 0. M2, no? The second row. I don't know why this stuff wants to be always smart about structure and structure. Then we can use a matrix K. Again, I use, okay, the notation that is here, M1, M2. Now I'm going to put this one, K1, K2, and this one here, no? All right. So let's see. I'm going to have here, I'll use this one. So I'm going to have K equals to K1 plus K2. Let's make it general. K1 plus K2. And the second row would be negative K2 space K2 plus K3. Okay, I mean, we can leave this. Okay. So for our problem, what do we say? M1 equal to M, no? M2 equals to. Yes, you have a question? Let me look at it. It would be K1 plus K2. Oh, yeah. Minus K2. Correct. Yeah, correct. So we have this, and then, I mean, we say this one was equal to M. Then what do we say? K1 equal K, no? K2 equal K, if I remember right, and K3 equal to K. I mean, see, I'm working backwards everything, and then we say in this one that M was equal to 1 and K was equal to 1. Okay, so let me save this. I don't know what I need to save this, so it looks like I'm saving all this stuff here. Okay, so this will be, let's say, again problem. I'm going to solve this one. Again problem, I save this file as. Okay, so now it's going to be very simple. You can type over here. You can type anything you want, really, but let's say, let's type over here mode shapes. You can do differently, or eigenvectors. Comma, let's say here natural. Natural. Okay. Frequencies, I'm probably going to put the N in capital N. Should be equal to the eigen problem of K comma M. You can do this different ways. Hopefully, they change the eigen function all the time, so hopefully this is going to work. Otherwise, I'm going to have to do a help, but that should work. So let's see if I run this. Hopefully it's not gonna give any error. Here we go. So now this becomes a bit confusing. Okay, I'm probably gonna just write this down, but basically you see that you type this stuff and it's given two matrices, one called mode shapes or eigenvectors, the other one called natural frequencies, so will be eigenvalues, no? Okay, so these values over here corresponds to what? This value here will correspond to what? Lambda 1 squared, no? And this value will be lambda 2 squared, no? Okay, so let's just say here from this way. Okay, so let's over here just because you could do all this stuff by hand solving the quadratic equation, okay? And now you could do this stuff. So let's say using MATLAB. Okay, what do we find? We found that lambda 1 squared equal to omega 1 squared, which is the natural frequency. The first one is equal to 1. And remember, the units for this should be radians per second, no? Okay, and we find that lambda 2 squared equal to omega 2 squared is equal to 2.5, no? Yeah, 2.5. Radians per second. Okay, so now let's go very quick here. Let's see what will happen. I'm going to do very quick, but tomorrow I will redo all this stuff. Let's say that we have to use this equation here, okay? Yes, so let me just write it down over here. We had x2 over x1 for 1, okay? So let's say I use the first one is equal to minus m1 lambda 1 squared plus k1 plus k2 divided by k2, no? Okay, so let's see. Since this one is easy, so we say m1 is equal to 1, lambda 1 is equal to 1, so this value will give you what? And k1 is equal to 1, and this one is equal to 2, so this will give us what? Minus 1 plus 1 plus 1 will give 1. Yeah, okay. And what is K2? 1. So basically here what do we get is that as we were expecting is that at that frequency, at that natural frequency, x2 over x1 for the first mode is equal to 1. All right. However, the MATLAB is given what? That the mode shape for the first one. So basically, if you do now look at the MATLAB. Okay, so the first column corresponds to the first eigenvalue, no? 1. What value is it giving you here? Negative 0.5774 divided by negative 0.5774. Okay, if you do that, this will be equal to what? 1, no? But it didn't give us 1 right away. Okay, actually it could give any value over here. Okay, so maybe we have time. Let's see if we can do the second one, no? All right, second one, we might need a bit more of math. I'm gonna need your help here, probably. Or you can do it faster than me. So let's say from math, we have that x2 over x1 for our second mode is equal to what? Minus m1 lambda 2 squared plus k1 plus k2 divided by k2, no?
since you have the computers, can you please do this one, put lambda square equal to 2.5 and tell me what is this value equal to? So it would be 1 negative 1 times 2.5 square plus 2. What do you get? This one. Well, M1 is 1. Why do you change stuff?
Like that, and I got.
Oh.
Uses N to.
Oh, maybe you sound for the equation?
Yeah.
Oh, you might be right. Hold on 1 second. I didn't check. I just copied the one. No, because I only use the first one. No, it should be still M1. No, nothing changes. I think that changes the value for lambda. It is if you use the other term.
Oh, okay.
Because you can use either one. You see here, you can use either this one or this one to find it. I'm using that one on the right. No, but good question. So what do you get? Come on, guys. 7.25 for the top. Okay. Can somebody double check? Positive, remember you had a negative here, no? It's still. Wait, no, why do you put a square? This is already 2.5. Yeah. No, because we use the 2.5. Sorry, it's my fault, maybe. So what do you get then? Maybe I could do it by, I mean, then it's easy. Why do I need that? So will be, this one would be minus 2.5, no? Plus 2. So will be negative 0.5, no? Over 1, no? Okay, so you see, I was trying to make it complicated. So this basically is going to give that x2 over x1 of 2, oops, should be equal to what? Negative 1/2. Which basically this will mean what? That when x2, so x2 will be moving twice as x1, no? Yeah. So when x1 is moving 1 unit to the right, x2 will be moving 2 units to the left, no? Okay. So that's what we get. However, the MATLAB is giving us what? It's giving us what? So it's giving us the negative 0.8165 divided by 0.4082. But if you simplify it and find out that this is twice as the other one, so it should give you negative, again, the negative minus 1/2. But why? So I just want to finish with that. Why is MATLAB giving us a different value? Or we are getting a different value? Because really, these values here, when you say 1 minus 1, or this one is moving 0.85, or this one is moving whatever, negative 0.85. The eigenvector problem is not telling you how much the block is moving to the right or to the left. It's not telling you, for example, it's moving 2 inches, 3 inches, or 5 inches. It's just giving you the information about how that system is behaving. Correct? Moving to the right, moving together, not moving together. The exact amount that is moving will be given by what? Will be given by, I mean, it's going to depend on what? Remember when we did the same thing on the initial conditions, no? Okay, if you displace it at the beginning 1, it's not going to evaporate the same thing that if you displace it, let's say 10, no? Yeah, so the real deformation will depend on the initial conditions, but the general behavior of the system will be given by the eigen problem, okay? By the modes of frequency or mode shapes. All right, so we stop over here. You have any question? This concept is so important for many classes.